Okay, so welcome to this ISM seminar. Today is really a pleasure to have Dmitri Yakovlev from TU Dortmund, and we know each other since many years, and then I appreciate the work Dima is doing many years, and recently he was touching the field of perovskite, contributing to development of the field, especially in the direction of physics, the direction that we like a lot, also to explore and to further development. So this seminar is, beside the seminar, is also a starting point for further collaboration with Dima. And also I welcome Michael Nestoklon, who gave a talk this morning in the Department of Electronic Engineering at the University of Rome Tor Vergata, and many of the theoretical activity on this topic has been also developed, is under developing also from Michael. So we could have, during this day, they will stay with us today and tomorrow. We could have these days also fruitful discussion with both of them, I mean, to further develop this activity. I know some of you were proposing some activity on spin, on perovskite. I believe today we will have a lot of this information, and then I'm very sure that will be many kind of possible collaboration. Dima, thanks a lot for accepting the invitation. It's really a pleasure to have you.
Hello, Alda. Thank you very much for inviting me and Mikhail here. It's really a pleasure to visit your labs, to be familiar with the facility and things which you are doing here, and especially to be familiar with the people, because one of the main points of this visit is to establish collaborations with your institutions and with the colleagues here. And I'll take this chance to present our part of the spin physical study in the spin physics in lead halide perovskites, crystals and nanocrystals. The field with which we are involved the last 6 years. Actually, in TU Dortmund, we are experts in the basic physics related to the optics and spin phenomena with the semiconductor nanostructures, quantum dots, quantum wells using the time-resolved spectroscopy. Typically, we're using liquid helium temperatures to have better lines and strong magnetic fields up to 10 Tesla in our labs and up to 60 Tesla in the external facilities. And since recently, so we turned to the perovskites, and I think that I can skip the motivations for you for what the perovskites are good. So I wanted to make kind of the initial presentations with some list. It would be on the next slide, or the differences, or I would say what's happened if the scientists from the common semiconductor research comes to the perovskites. Yeah, what surprised them, but what not surprised them. So actually, we're talking about the lead halide perovskites. The materials are presented here. We have a great selections where the lead is the main hero, because lead is present in all these materials, and also lead controls the band gap energies, both the top of the valence band and the bottom of the conduction band, with its orbitals to contribute it. And then we have a selections of the halogen ions. It can be iodine, bromine, and fluorine, so it allows to tune the band gap in the wide respect, but in fact not influences too much on the spin properties. And there is the cations, which are sitting here in the cage. It can be either cesium for fully inorganics or some organic molecules. So we have a playground with these materials, and our task was to see, to learn how the spin physics or spin phenomena depends on when we exchange the different components. When we start this field, so we have no knowledge about the spin physics, and actually there was only few papers about the spin physics. There are not much more papers by nowadays, because only few teams in the world are busy with this field. Well, I find it very exciting. Why perovskites? Or this is a comparison of the perovskites against common semiconductors. What we typically get used is gallium arsenide, cadmium telluride, zinc selenide. All these semiconductors has a zinc blende structure, and this is the band structure which is here. Conduction band is simple with a spin 1/2, but valence band is already complex with the spins 3/2 and 1/2, and there is a spin orbit states for the holes. And actually, if we're dealing with the spin physics in the common semiconductors, a lot of complications come from this complex valence band, because the whole states are mixed with each other, so the spin relaxation processes are very fast. You can split them in the quantum wells, you cannot split them in the quantum wells. And spin relaxation is fast, and the many processes are limited by this. Also, if we wanted to make a full optical orientation of the spins with a circularly polarized light, I will talk about this more in detail. In this complex structure, you cannot reach the 100% circular polarization, optical orientations by the excitation. If we go here to the perovskites, so we take these bands, and it looks like we flip them over, but also they push these complications of the holes. It's now this heavy and light electrons band, but they split off by the very large energies, about 1.2, 1.5 spin orbit interactions. So what we left with this simple bands, which is very good and very easy for making spin physics in its ultimate appearances. But it happens also more, because now the valence band orbitals are formed by the s orbitals, or the lead ions, not by the p orbitals like in the common semiconductors. And the conduction band is formed by the p orbitals. And for the spin physics, it becomes very important, because in spin physics, we have also interactions of the band carriers with the nuclear spins. And if we wanted to have the maximum of these interactions, we need to have s orbitals, where the carrier has a maximum of the nuclear. It's known for the gallium arsenide, for example, whole spin hyperfine interactions for the hole with the nuclear is nearly 0. And it will be other way around, the maximum in the perovskite materials. So there are a lot of, I would say, differences and motivation, which position lead halide perovskites as a very nice model materials for the spin physics, for the spintronics, and the things which theorists predicts, which can be realized in the semiconductor physics. Because theorists sometimes, often they look broader on the field. They try to play with the different parameters, because it doesn't cost them to reject these parameters. Now these experiments or these suggestions of the theories can be realized and can be checked for the perovskites. So this is a list of the differences and common things when I compare perovskites with the common semiconductors. So we have inverted band structure already discussed. Effective masses are rather comparable, O2 and perovskites, so it's on the same level. What is really different is the very low mobility. Of course, when I come 5 years ago on the conference of the perovskites, I was shocked, because every second talk was about the giant mobility of the perovskites, number of 100. I was missing the point. 100 millions for normal semiconductors is a giant mobility, but not 100. And I was told that the field is very much originated and populated and made and driven by the people from organic semiconductors, which 1 is large, 10 is huge, and 100 is colossal. Something like that. So it's a very different scale. But also for semiconductor physics, or for us, it takes, we see it. So we in some respect, benefit, in some respect, suffer about that. Where it becomes very convenient that, in fact, we have a coexistence of localized electrons and holes when they're photogenerated. Again, I mostly talk about the low temperature physics. The carriers are localized on the fluctuations, mobility is low, and the electrons and holes are sitting not far from each other, but in the different places. They are not recombined. But in fact, if you work with such materials, you work simultaneously with the N-type and P-type material. So we see signals from electrons and from the holes from the very same sample. We do not need to run to technologists and ask, make a bit more N-type or a bit more type. Okay, the drawback is that we need to recognize between these signals in the experimental basis. Magnetic fields helps with that. I will show that. Exciton binding energies are in the reasonable range, 10 to 50 millielectron volt in bulk, and can be hugely enhanced in nanocrystals or in the two-dimensional materials. High concentrations of defect. Material is fragile, it's sometimes not easy to handle them or even to polish. And surprisingly to that, all the high presence of the defects, the materials has a very high quantum efficiency. Emission is incredibly strong. And this is explained by the defect tolerance, that the defects do not like to be within the band gap, they're outside the band gap. And that's why if Kerr is relaxing energy to the band gap edge, the only way for this Kerr to go out is to have a radiative recombination. Low stability and ambient conditions due to organics components. Non-organic semiconductors are more slow, but in this case, I would say that low stability is detrimental maybe for the applications. For the basic research, it's sufficient for us. So we have organic semiconductors with which we work during the year or 2 years and so on, and then they do not degrade it too much. Good optical properties, surprisingly. So at low temperatures, the exciton resonance can be only 1 millielectron volt. So one can, if we make a single crystals, I'm talking not about the polycrystalline films. So the nice spectroscopy can be done on these semiconductors, and also nanocrystals and two-dimensional materials are available. In fact, if we go through this list without starting the spin physics and asking me what I think, whether it would be reasonable to start or not, I would say it would be difficult. So many defects, scattering, maybe in localization, nucleus. So I would expect that spin signals will, spin relaxation times should be very fast. Maybe spin signals will be very small. So it should be difficult to go ahead. And surprisingly, when we start with these materials, we find that most of our magneto-optical and spin-dependent techniques are extremely easy, give a huge signals in the perovskites, and the perovskites are extremely friendly to this spin physics. So, and I wanted to show today a few examples to you how it works and what information one can get out of that. So if you have questions, you can break me during the talk, so feel free to that. So what I wanted to present today, how these perovskites, why they're good for the spintronics and the spin physics, and to present several experimental techniques: time resolved pump probe, Kerr rotation, spin flip Raman scattering, polarized optical orientations. And as I say, I will talk about experiment mostly at the low temperatures, cryogenics one, but show some examples also up to room temperatures. We use strong magnetic fields up to 10 Tesla or pulse fields up to 30 Tesla, time resolutions of 1 picosecond, and high-end spectroscopy resolution. So we need sometimes huge spectrometers for that. Just to explain why we're doing that, one motivation was that this is an interest in subjects, and another motivation is that we have a responsibility in TU Dortmund before the colleagues who were starting this field in Dortmund. Actually, the first paper on the exciton in the perovskites, in cesium lead bromide and cesium lead chloride, was made in Dortmund in 1978. So this is the measured spectra, and the first band gap calculations also was done by Trojan. So then Dortmund is proper place to continue. So if we talk about spin physics, where are spins? Spins are in the several systems. So we have excitons, electron hole excitations. They're short-living, typically in perovskites 300 picosecond. And we have electrons and holes. So in this respect, excitons can be broken, electrons and holes can be localized in the different places and live for the very long time. So in perovskites, we will show that at low temperatures, it can be up to 1 millisecond lifetimes of these carriers. And excitons and electrons and holes, we can generate by polarized light, circular polarized light. So they will be oriented, their spins will be oriented by light. And also we can read out their polarization by emission, so we can understand whether they are still polarized or not. But we have also spins in the nuclear spin system. In lead, for example, 20% of the lead has spin 1/2. And this system is not addressable directly by the light, but you can polarize the system through the carriers, and you can read out about polarization of this system through the carriers. One can also apply radio frequency in the conditions of the magnetic resonances and erase the nuclear polarization. So you can learn also what's happened with the nuclear spin system. And the nuclear spin system is important for the spin relaxation processes of the carriers. So I will show how this spin systems can be addressed in water experiment and how it works. So, but before, no spins in this slide. It's just an example of recombination dynamics. So we use this component. In fact, it's very close to the FAPI with the small compositions of cesium and bromine because it stabilizes these materials. I think as technologists, you are very well known that this is the best compound. So it's a black perovskites. And this is the low temperature spectra. The green line is absorption, nice exciton resonance we see here. If we make a CW photoluminescence, so continuous wave, then the line will be the blue one. So it has 5 millielectron-volt Stokes shift from the exciton resonance. But if we use time resolution, so strict camera, we excite with 100 femtosecond pulses, and here measure on the image how the photoluminescence decay with the time. And we measure on the very first time moments, first 20 picosecond. The photoluminescence will be here. So exciton recombine very fast, and then the recombination is shifted to the lower energies and is contributed by excitons, bound excitons, electron-hole pairs. So we're still not very firm what are the processes which are contributing here. And one can see that recombination dynamics has a fast component of 50 picosecond, which turns to 900 picosecond. But if we measure to the longer times, we can reach it up to 100 microsecond in this case. So this 100 microseconds comes not from the excitons, but from the carriers which are separated far from each other. And either they have a small overlap of their wave functions, or maybe they jump out and then move to one another in the structure. But important for us that we have resident carriers with a long-living carriers here. And this is also convenient and make strong spin signals. One of the technique which is very often used for the spin physics, or actually many of the spin experiments are based on that, called the optical orientation techniques of the carriers. So the idea of this technique is shown here. What we do, we come with a laser light and we excite hole from the valence band to the conduction band. But if we use this light circularly polarized, for example, sigma minus, then this photons brings moment -1, and it will generate hole with a spin -1/2 and electron with a spin 1/2. So just using this circularly polarized light, we will photogenerate spin-oriented carriers. And if this spin orientation is not lost by some other mechanisms, when we can wait until recombination, this electron will recombine with this hole and it will emit sigma minus polarized light. And we can measure the degree of the polarizations and to see how much spin relaxation happens, not happens, or change temperatures, magnetic fields, and play with that. Of course, if we come with a sigma plus polarized light, we will make an opposite orientations of the carriers. How it works for the perovskites. So again, we have this as material close to FAPI. And now we focus on the excitons, the first 50 picosecond window. So on this emission, we excite sigma plus polarizations, and then we measure with the time resolution sigma plus component and sigma minus component. And one can see here that sigma plus component is much stronger than the sigma minus. If we calculated the polarization degree here, or the optical orientation degree, it will be called in this experiment, we reach 80%. And with the time, this 80% decays only to 60% and then stays high. And ultimate limit for the optical orientation is 100%. So we're very close to it. Another surprise in this experiment was, okay, the first surprise that we can reach very high optical orientation degree, but this one can predict from the simple band structure that we have only spins 1/2. But another surprise comes when we start to move our laser from the nearly resonant excitation of exciton to higher and higher and higher energy. And here you see this optical orientation degree of 80%. It stays constant without decaying nearly up to the union of 1/2 electron volt. For the common semiconductors, it's very unusual because in the common semiconductors, there is a spin splitting, Yakovlev mechanisms for the higher line states, and the spin relaxation here is much more efficient than on the bottom. So the relaxation by acoustical and optical phonons will nearly destroy your optical or spin polarizations. Here, we have no distractions at all. So it starts to decay only after 1/2 electron volt and disappears to 1 electron volt.
How many Tesla are you working in?
No Tesla at all. Zero magnetic field here.
Zero.
It's zero magnetic field.
There is an instant.
This is another thing. This is so-called Hanley effect. 0.4 Tesla. You want to check it for the spin relaxation mechanisms. This is a zero field data. But why this decay happens then? There can be two reasons for that. One reason that some spin relaxation really starts for these high line states. And another reason is that when we excite so high, our band states are not so pure. So we have this 100% polarization for generation of the spin, only for the states closer here. When we go to the to the larger K vectors, where it mixed another band, and generation mechanisms are not so pure. And then we come to Misha-Nistaklon, and he calculated this. So this is the band structure counted R minima and M minima. And he really calculated that when we go up, then some detuning of about 1 electron volt became detrimental for the generation efficiency. So actually, we may conclude that the effect of this decay, what we observe, is fully aligned on the generation efficiency. And in principle, this is also the way to explore the band structure up to 1 electron volt up. Yes, if we can look and refine parameters, how this mixing happens. Another things which we also check here. So if we have no relaxation, so it's again, this is optical orientation degree as a function of the detuning. So we have no spin relaxation for these materials, no decrease of optical orientation degree up to half electron volt. That means that there is no spin splitting. And this spin splitting, this is the point which is discussed quite broadly for the perovskite community, the so-called Rashba or Driscoll splitting. Actually, the effect comes due to the strong spin-orbit interaction. And it comes in the materials in which the inversion symmetry is lost. So in this case, if inversion symmetry is lost, then the bands for the spin up and the spin down are not, doesn't have the same energy. They are split in the energy. And this splitting should get a strong effects for the spin relaxation. But also it's discussed that such a splitting may take effect on the recombination because you go to the quasi-indirect semiconductors by this means. If you are just coming to the conference or looking through the papers, I'm talking about myself. There is tons of the papers, and you have an impression that giant Rashba effect present in perovskite semiconductors. This is well-established facts, no doubts. There are some people experimentally used to explain their surprising experiments, some not. But in fact, when you look very careful to these papers, you understand that in these papers, theoretical papers, predictions, there is small if. If is that it's not sufficient only to reduce the symmetry, for example, from cubic to orthorhombic. This doesn't remove the inversion symmetry. You need also to find some mechanism which shifts the atom in the middle to one of the side and which reduce the inversion symmetry. But whether this if happens or not, what this if happens for the bulk materials, or maybe on the surface it may happen, but for the bulk material was not clear. At least what we make here in this experiment, we compare these FAPI materials, which is about cubic, with the MAPI material, which is orthorhombic and strongly anisotropic at low temperatures. And we find out that optical orientation detuning here is exactly the same. So we may claim that at least for the bulk perovskite, we have also examined two another materials I didn't show here, that at least for the bulk perovskites, the inversion symmetry is not lost, and this is Rashba and Driscoll splitting are not in the game. For two-dimensional or for the surface, it of course may come.
And organic molecules do not play a role? I mean, if this was mainly organic fabric.
We're dealing with the crystals, nanocrystals, so it's really thick crystals. Even if something happens on the surface, the signal from the surface is much too weak compared to the signals which comes from the depth of the semiconductor here.
No, I mean, so if you have cesium in the center, it's, I can easily imagine the inversion symmetry. But imagine you have from a medium, a cation, which is by itself is not symmetric. I mean, so in that case, I mean, we can still we still have inversion? Probably the inversion signal is related to the lattice.
I think that in this case, with the small organics materials, what people start to discuss is so-called dynamical Rashba effect. They start, and this molecule starts to rotate. It can induce some asymmetry at certain frequency, but still, what at low temperatures we observe when these molecules are frozen, that the appearance doesn't tell us that some spin splittings are present in the crystal. I would say that the result which you have shown, it's not the closing the problem, it's just one of the steps to show what experimental ways we have to examine it.
Okay.
So another techniques which we use for the experiment is the so-called pump probe Faraday rotation technique. It's pump probe where the pump is circularly polarized. So this pump photo-generated spin-oriented carriers. And then we use the Faraday effect to test this spin polarization when we send linearly polarized light. And you know that if you send linearly polarized light through the magnetized media, the polarization plane will rotate. Actually, we measure the rotation of this plane, and we change the time delay between pump and probe pulse. So the duration of the pulses is 1 picosecond. Typically, pump pulses comes here, and then one can observe the decay of the polarization in time. This is without magnetic fields. If we switch on magnetic fields, then picture became switcher, because this spin's perpendicular magnetic field is applied, starts to rotate about the magnetic field, and the signal precesses. So actually, this is the Larmor precession of the spin. From period of this precession, we can directly measure Zeeman splitting, or the Lande G factors, and decay of this signal is the so-called spin dephasing time. There is spin relaxation time when we talk about the single spin, and spin dephasing time is when we talk about the decrease of polarization of spin ensemble, because spins may precess on the different frequencies, and so how it works with the FAPI crystals in the experiment. So this is the dynamics which is measured, and typically in such a dynamics one can observe one precession signal. But here you see that in the experimental signal, two precession frequencies are present. Here they're decomposed for the Hall and for the electron precession frequencies. And this is exactly the case and specifics of the perovskite semiconductors, that we have electrons and holes sitting in the same material in different places. We polarize them, and then we can observe their spin precession. And the times we observe them goes beyond 2 nanoseconds, so it goes much beyond the exciton recombination time. It's really resident carriers. We can plot the frequency of the precession as a function of magnetic field and evaluated G factors. The Zeeman splitting is 1.1 for holes, 3.5 for the electrons. Next thing, so except of the electron spin systems, we have also nuclear. So this is the spins of the nuclear, which are sitting here. And the carrier, which is localized, it's interact with a few nuclear spins from 5 to 20 or 200. And these interactions have an effect on the spin polarization. It has effect in a way that we have a carrier spin system and we have a nuclear spin system. If we spin polarized carriers by light, these carriers can move their spin to the nuclear spin system, and nuclear spin system becomes polarized. But if nuclear spin system is polarized, it can play back with their polarization and effect on the carrier spin system. So it's like we can generate a photo-induced additional component of the magnetic field in the crystals, which is add up to external magnetic field. And one can measure this component. It's measured here. What is shown here is a pump probe dynamics. So we should take care about the precession period here. And in one case, we use a tilted angle here. Tilted angle we need in the case that the nuclear polarization is induced not perpendicular to the external magnetic field, but with some angle to the magnetic field. And if we use sigma minus orientation, then nuclear field Pn is subtracted from the external field. So the period of precession becomes larger. If we use sigma plus polarization, so it should be sigma plus here, I don't know, it's somehow missing. Then the nuclear magnetic field is added it to the external field, and the precession becomes faster. And the difference between these precessions depend on the power of excitation, because the more power we pump, the more nuclear systems will polarize, the more effective nuclear fields appears. So what we find out here in this experiment, this is dependence of the effective nuclear field for the holes and for the electrons, increasing with the power. And we have external magnetic field of 100 millitesla, and for the nuclear field for the holes is minus 50 millitesla. And for the electrons, it's about order of magnitude smaller. And this is, we understand why, because it's really specifics of the perovskite materials that valence band is contributed by lead orbital, s orbitals of lead. It has stronger hyperfine interaction with the nuclei, and in conduction band, this hyperfine interaction is weak. One can also, in this experiment, apply radio frequency. What does radio frequency? It comes to the resonance. We also scan some magnetic fields, and we apply we scan also, say other way around. So the experiment is like that. So we set some magnetic field, and we scan our radio frequency in a way that we find that the frequency where the radio frequency erase the nuclear polarizations. It's like a magnetic resonance conditions, but we did optically detect this magnetic resonance. And from this value of the Kerr magnetic ratio, we can say that this is really corresponds to the lead to 207 isotopes with the spin 1/2. So this pump probe Faraday rotation approach, it can be not applied only for the bulk single crystals, but also for the nanocrystals. This is example of the cesium lead bromide colloidal nanocrystals, 4.6 nanometers. And in this example, we show that these nanocrystals can be run at room temperature for the spin coherence with a pretty long. So this is 200 picosecond spin dephasing times, which is rather long if we compare with the 3.5 and with the 2.6 semiconductors. One can also apply these techniques for the two-dimensional materials. I show only example here. So this is the pair lead iodine, where the single layer of the octaheders of the perovskites is implemented, and these layers are not electronically collaborate with each other. The exciton binding energy in these materials goes up to 500 millielectron volts. So the materials became very much comparable with the transition metal dihalogenide, the materials which is many teams have started. So from the properties, it allows to go for the same physics and to the specifics of the perovskite band structure. And here also the spin coherence can be nicely absorbed. Reflectivity or optical orientation can be also done. I would not go much in depth for the low dimensional materials in my talk. Another techniques which can be applied to study spins is the spin flip Raman scattering. So I guess you know what is the Raman scattering is. So you excite some electronic state in material solid states, and then you have an emission of the phonon. So the light is scattered with the emission of the phonon. Typically, these are optical phonons in the range above 10 millielectron volt up to 100 millielectron volt. But you can use these techniques only to study small Zeeman splittings, for example, for the excitons and for the carriers. So in this case, we resonantly excited exciton resonance, and we apply magnetic field. So we have a Zeeman splitting in magnetic fields, and these Zeeman splittings are rather small. So in our magnetic fields up to 10 Tesla, they're in the range of 0.1 to 2 millielectron volt. So we need a huge spectrometer to play several tricks to subtract the reflected light or the laser line, which is strong itself, but it's doable. And what we observe that the scattered light has not the laser energy, but it's shifted by Zeeman splittings. So like the laser light is here, and we have a Raman shift by the Zeeman splitting. One can play also with the different geometries, Faraday forked, and analyze the polarizations for that. But I will show just one example, how this spin flip Raman scattering spectrum looks for the cesium lead bromide. So the whole range here is 2 millielectron volts, so we are very close to the laser line. Magnetic field is 8 Tesla, and we observe very pronounced lines of the whole spin flip, of electron spin flip. There is exciton spin flip, and there is also the double electron spin flip. If we change magnetic fields from 0 to 10 Tesla, one can see that these shifts are linearly shift with the magnetic field, as one expects for the Zeeman splitting, and we can determine these G factors. So for the exciton process, for this one, this is flip of the exciton as a whole, electron and hole flip the spin to the opposite, and this gives Zeeman splitting. But for the electron spin flip, the process is like that. So we have a resident electron in the crystal, we photo-generated exciton, electron flipped spin, and exciton delivers energy for that. So in the scattering of the exciton is missing the electron spin, or for the hole it's the same. Kind of surprise for perovskites was also that we observe not only the single spin of the electron for the hole, but we observe also the multiple spins. For example, the 2 electron spin, or electron plus hole, electron minus hole. It means that the exciton, when it's photo-generated, interacts not only with one resident carrier, for example, electron. It has also its orbit, or at least a tail of its orbit, hole spins. So the 2 carriers have a chance to make a flip. And this also tells that we have quite a concentration of the resident carrier in the semiconductors. So sometimes we can can detect the process where the 3 particles are contributed, 2 electrons and 1 hole. And now in the last part of my talk, I'll turn to the Lande G factors evaluations. And this is a slide to explain that this is not only the Lande G factors is a very important parameter for the spin physics because it's control the splitting of the spin states in external magnetic fields. But it can be also useful for solid state community broader, because if you look on the equations how these G factors are composed, you can see easily that they're composed from the very same parameters like where effective masses are composed. So the band structure parameters, splittings, or some parameters which are controls the band structure, they're very much the same. So in fact, if we measure G factors, their anisotropy, their values, we can get an information about the effective masses. And this is especially important for the perovskites, where the mobility is low, and measuring effective masses by the cyclotron resonance, for example, doesn't work. So it's still open questions how to do it. So here we can get a valuable information. What we do, we study different perovskites materials, single crystals are shown here, where the band gap is changed from 1.5 electron volt up to 3.2 electron volt. So he is more chlorine-based, he is iodine-based materials. This was kind of the work implemented in this structure because some of the materials are nearly cubic, so it's sufficient to measure one component. But some of the materials, like for example, MAPI and cesium lead bromide, they're anisotropic. So we need to measure all directions and also take into account that G factors can be anisotropic. And then our main question is that whether we can have for this material class some systematics. And systematics in a way that the G factors depend on the band gap. And if we plot the G factor as a function of the band gap, the anisotropy are shown here by symbols of the different sizes, but one can see that it can be very systematic. For the electrons, the G factor is going down with increasing band gap. And for the holes, it starts from the negative value, cross the 0, and then grows up. And solid lines here are calculations, which are tight binding calculations done with Michonist-Taklon, and they were also improved by KP theory with these parameters. And it was surprising for me, maybe for theorists also, that the very same set of parameters, like spin orbit 1.5 electron volt, matrix element 6.8, and this is contribution of remote bands, allows to describe the whole class of the perovskite materials in the sense of the G factors. So this is an example when we measure anisotropy. So we apply, so this is a cesium lead bromide with the C-axis. In these directions, we can apply magnetic field parallel to it, perpendicular to it, or to make some angles. And we observe that the electron G factor decreases its value, hole G factor increases this value. What is interesting happens here, that the exciton G factor, which is the sum of the electron and the hole, it becomes nearly isotropic. And this is kind of like a, I don't know, thumb rule for the perovskites. Whatever you do, we do with the electron and hole G factors separately. When they put together, they give you the same isotropic value. So this is example that we measure exciton G factor up to 60 Tesla in pulse magnetic field in Los Alamos. The dependence is very straight, non-monotonously. It's also result that the bands are very simple, so there is no admixture of the additional bands even by such a high magnetic fields, that the spin orbit state is far away. So if we sum up, okay, this is about the bright exciton G factor. Yes, if we take now and look how the G factor for electron behave on the band gap, so it decreases. G factor of the hole, it increases. But when we sum them up, we find out that the sum is about constant on the level of 2.3. So if we wanted to know what is the G factor of exciton is expected for any materials in this range, for the perovskite, so with the high accuracy, it's 2.3. For the dark exciton, the situation is different. So it's not nearly the constant, it changes very strongly. And for the dark exciton, which is a different of electron and hole G factors, the dependence is strong. So, and this is strong difference between bright and exciton G factors give a good playground for the spin physics, because you can go in one range where one is larger than another or equal to each other or goes in the opposite directions. Now, what's happened if we go from bulk materials to nanocrystals? And in this case, again, Misha Nistaklon make a calculation of that. And he says that additionally, in nanocrystals, additionally, there is an admixture of the spin orbit bands, which was absent for the bulk materials, for electrons and for the holes. And this admixture make a strong changes for the G factors. And the predictions is the following of the theory. So the dashed line here is what we expect from the bulk as a G factor as a function of energy. Now we can change the energy by the different way. For example, we take cesium, lead, iodine nanocrystal, very, very large nanocrystal, it would be here on the bulk value. And now we squeeze, reduce the size of the nanocrystals, then confinement energy will be changed. So actually we will increase the energy due to confinement. And we see that first expectation that we should follow the bulk trend. It's not working. So we have a theory predicts much stronger dependence. For nanocrystals, cesium lead bromide or cesium chloride, so again, for the electron G factor, much stronger changes are predicted due to the mixing of the spin orbit bands. But for the whole theory predicts very weak changes. And we check this experimentally on the cesium lead iodine nanocrystals in glass. And for the large nanocrystals, we observed that these predictions are really works very well. So the electron G factor goes much faster than the bulk. Hole G factor stays nearly constant. Now we have the data which I wouldn't show today, that in fact the hole G factor starts to deviate under strong confinement from the theory predictions, and we need still to understand what additional states need to be mixed to go for that. So in fact, measuring of the G factors give a rich information for the band structure theory and calculations, and hope that it can help to refine these parameters. So this is a summary of my talk. So my main motivation or my main goal was to convince you that experimental methods of spin physics are well working for lead halide perovskites, bulk nanocrystals, and two-dimensional materials. That perovskite semiconductors are really new model systems for the spin physics. And this material demonstrates very bright spin phenomena with the properties which are very much comparable in the parameters with the 3,5 and the 2,6 semiconductors, which we have studied there far. In some sense, they are going beyond. So the typical spin relaxation times or parameters which we observed are very much comparable to what are known for the 3,5 and for the 2,6 nanocrystals. So this is publications which we worked out so far, and one can see from this list that we start in 2017 with one paper, and then it takes 3-4 years for us to understand how to work with the semiconductors, despite that all experimental methods works very nice. But the complicated picture, coexistence, electrons and holes takes time to get used. And then the more papers starts to be generated. And of course, this was results which was gained with a few experimental teams in Dortmund. and with the theory of Misha Nistaklon and Misha Glazer, who helps here. And I'm very thankful to the samples from ETH, Würzburg, and ITMO University. And thank you very much for attention.
We can see. So now it's open for questions. Switch on the light. Please, Padre.
Thank you for a very nice talk. At the beginning of the talk, you mentioned 80% spin polarizations in field-free conditions. But the measurements were done at 1.8 Kelvin. I was wondering, when does the spin polarization effect disappear? At what temperature, and what is the mechanism that kills the spin polarization?
The polarization starts to decrease after 30 Kelvin, sorry.
30 Kelvin.
30 Kelvin. It starts to decrease, but not because we lose in the generation efficiency,
Okay.
but the spin relaxations on the bottom mechanism starts to switch on due to the phonons. We need still to learn what mechanisms are really involved there and how they're important.
Okay. And the other question is, would you see the same effect in polycrystalline films?
Yes.
You don't need a single crystal, let's say.
No,
You can
no.
also do it on polycrystalline.
Actually, our experience with the perovskite materials is the following. So you have a different materials, like this optical orientation, pump probe experiments, Raman experiments. Surprisingly, you can go with the different materials, MAPI, FATP, cesium, lead bromide. The physical appearances or parameters or value of parameters are not different too much from each other. I mean, in the sense of the spin dynamics. So it tells that the carriers are already localized, and this is localization conditions, maybe contributions of the nuclear spins, which is mainly comes from the lead. Lead is a hero here, but lead we do not change lead. Yes, we change some other components, and lead also controls quite a lot for the spin dynamics. And same happens for the polycrystalline films. We lose spectroscopy. We have, instead of 1 millielectron volt line exciton, 20 millielectron volt line. But spin physics or spin relaxation channels will be comparable. Sometimes you have scattering on the domain walls in the polycrystalline film, so you can have a faster dephasing, slower dephasing, but not detrimental.
Yeah.
Hi. Thank you for your nice talk. I have just a few questions about, for example, you in slide 8, you presented for united bromide as perovskite, and in that case, you said that free carriers recombined in a lower energy with respect to the excitonic peak here. Yeah, more or less, that one here. The blue one is related to the free carriers, while the red one is related to the excitons. But generally, we have the exon that are at lower energies. Why does it happen here? I don't get the point.
No. So the exciton, free exciton, yes. Free exciton here corresponds to the absorption maximum.
Yeah.
So actually, the exciton is here. Now, at the low energy, you can have a bound exciton or localized excitons, or localized electron hole pairs, which are separated in space, maybe some donor-acceptor recombination. So you can have everything here.
So in that case, I'm not free carrier, I guess, because I understood that the thing that the blue line was related to free carriers, but it cannot be. Right?
There are no free carriers. No, the recombination is fast, but you can have carriers which comes from the excitons, which because we excite not resonantly, we excite somewhere here above. So excitons can be broken on the carriers. Carriers are relaxed, and then we have delayed emissions from these carriers.
Okay. Okay. So thank you. And another question was related to, I guess it was slide 10. And in that case, I guess so that, here you were able somehow to predict, maybe 11, sorry, but I don't remember actually, but it was related to the fact that there are transitions you can be selecting somehow, for example, valence band 1 to conduction band 1, and also valence band 1 to conduction band 2. But how can you discern if they are related to from inner valence bands with respect to the?
No, actually, in our experiment, we didn't touch these conditions of another band, or this M band we didn't measure. So
Yeah, but it cannot be from other valence band because generally the energy split between the first valence band and the other ones are lesser with respect to the higher valence bands.
No,
because of collection.
okay, let's clarify. This is bulk material, yes? There is no second valence band here, or it's splitted by, I don't know, 1.5 electron volt maybe. Yes, what we care, so there is no second band here, so this minimum, which is more than 1 electron volt. What we care about, this is spin orbit split conduction band in the air point, but this is also 1.1 to 1.5 electron volt. We didn't come so far with our experiment.
So I believe this will need to be discussed later on because we find some different band structure. So maybe we can discuss exactly the paper you published. Yeah. Okay.
Of course, it makes sense to go with the experiment here and to address, but in fact, for this, we probably need not to the bulk samples, but thin crystals. Otherwise, the absorption is so strong that and relaxation from these states to lower is also so fast that we lose information about these higher exciting states. Or maybe another methods like Raman scattering or second harmonic generation can help here.
Thank you very much.
Yes, please.
I'm wondering, I'm a chemist, I'm wondering what the organic matter, what kind of game does the organic matter play in this?
For spin physics, what we see, it doesn't matter whether you have cesium or organics. We didn't find the strong contributions or strong difference between fully inorganic or organic semiconductors. It may happen that we are working at the low temperatures, where also this organic, for example, rotation degree of freedom of this organic material molecules are frozen, and that they do not appear each other. Otherwise, only the structural phase transitions, but it's more size of the cation, as I understand. It's not so much whether it's organic or not organic.
That's for the bulk, okay?
That's for the bulk.
For small crystals?
For nanocrystals.
Small crystals. Nanocrystals.
For nanocrystals, we didn't study too much of organic, inorganic nanocrystals. What the results are shown today is for the inorganic nanocrystals synthesized in glass. So they are from the glass melt, from the higher temperatures are synthesized. But we have some measurements on the G factors, also on the solution-grown cesium lead bromide nanocrystal, and the results was very similar. So at least we know that the surface doesn't play too much role for the G factors or for the spin dynamics. Maybe for the internal degree of freedom, but we need to look carefully at this.
So FA or MA or PEA, PEA.
It seems that they do not contribute too much to the electronic states, like for the electrons and for the holes, for their localization, and the coupling with the nucleus comes not from this, for example, from cesium or from these organic materials. So the main contribution from nuclear comes from the lead, which is present everywhere. It's still very surprising things for me that we try so different materials and the appearances in experiment looks pretty similar or very close. If you take gallium arsenide just with a very different degree of doping, you will have much larger changes in the spin dynamics. Sometimes orders of magnitude. And here,
Just continue on this, just a second to continue this talk, because we have seen recently, we were discussing with Tommaso, many of the people, especially from the chemical point of view, chemists, they are moving now to introduce chiral molecules inside the crystal structure of the perovskite, let's say 2D with chiral molecules and so on. So do you think that, this could then impact the spin physics?
I think it depends how it works. If they do they kill electron hole pairs, both type of the carriers, or can they kill one type of the carriers or capture one type of the carriers?
Chiral, not so they chiral.
Yes, chiral for sure, for sure.
For bulk crystals or two-dimensional structures?
For two-dimensional, it should be a much stronger effect. For bulk, I would expect yes, but I would be maybe more cautious. So it depends whether these chiral properties of these molecules are transferred to the chiral properties or spin-oriented properties of the band states. My impression now is that this is electronic coupling between cations and the band states is not very strong. But it's also, it can be a bit tricky because I would say these chiral molecules may influence on the light which is going through the crystals.
Yeah.
Then, for example, this light will be circularly polarized even if we send non-polarized light. And then it will generate carriers, spin-oriented. So this is like not a direct coupling, but the indirect coupling through the light. Or either absorbed light or emitted light, the same.
Daniele.
That's, of course, very interesting topic to address.
Yes, a curiosity. There is some relationship between the carrier density, and these kind of effects. Let's say if you are above or below the mode transition, or if you excite above, resonantly with the exciton or above the band gap.
To excite resonantly or above band gap, we didn't see much effect. I would say it would be interesting to address this point by applying a gate to the structure, by controlling in this way. Because in our experiment, we even try to make an experiment with a laser and make an additional laser illumination to generate carriers. And we find nearly no effect. My explanation is that the localization of the carriers is strong and that we are saturated already at the very low level. Even very weak illumination, like daylight illuminations or some dark illuminations in the lab, is sufficient that we come to the saturation effects of the maximum of the carriers. And if we generated more and more carriers, they're closer to each other, they recombine. So it's like a self-adjusting process. By light, it does seem that it's easier to tune the carrier concentration.
Okay. Because when you show that the excess of energy effect in some way, the percentage between sigma plus and sigma minus. In this kind
That's true, but this is loss of the spin. So it's not loss of the carrier concentration. It just
no, but the carrier concentration, can modify also the structure of the band and so on.
Typically, when we measure, for example, power dependence or the emission intensity of our laser, it goes like a linear. There is no non-radiative channel, so we do not see that the spectrum reconstruct very strongly. Where we observe the changes at low temperatures, that, for example, delocalization may happen. Yes, that we, for example, have at low excitation densities, more localized carriers, and then it goes towards excitons. But it's simple heating effects more than the concentration effect.
And this mainly in crystal, probably, not in thin film made by solution process.
Yeah.
Probably this is.
Yeah, but for luminescence measurement, you have a regime, and if you want to perform pump probe, you need to excite a lot more. So the condition, the excitation condition,
okay, actually,
it's quite different.
It depends. It's bright, the signals are strong. We do not go too high, so you can go with it's pulse laser, but you can go with a 1 milliwatt of excitation. Or for the pump probe experiment, signal is huge. So we are not overdriven the semiconductors. For room temperature measurements, some people report also spin physics, but their spin physics reported under highly driven conditions. And then spin relaxations can go to 3-5 picosecond instead of 100 or 500 picosecond we observe here. But here, one really comes to the collective effects.
Yeah, please.
Just a curiosity, have you any information about the contribution of angular momentum, orbital angular momentum to the magnetism of the perovskites? I mean, for instance, for 2D, maybe it is not negligible for the perovskites.
But okay, the questions. What you talk about this angular momentum, because in fact, when even this yes, this scheme were driven, yes? So because in gallium arsenide, this conduction band will be just the spin state with orbital momentum 0. In perovskites, in fact, it comes from the G. So it's from the G1 half, and then this is G1 plus
So
spin 1 half, and then this is the spin orbit state.
A pure contribution of the angular momentum. So I have
At least
in mind what you get from circular X-ray circular diagram. You can split the atomic angular momentum in the orbital part and the spin part. So this is only an analogy.
In our optical experiments, it typically doesn't come out. Maybe I'm not expert in that, but at least what we observe by our methods, we never touched that. For example, in the 3-5 semiconductors, you can really decompose them by light, by band excitation. One need probably another laser, okay, far-infrared laser or synchrotron lasers or Röntgen lasers that really touch this moment for intraband excitation.
No, maybe you have some information about some other experiment. For instance, is there in the literature any extensive experiment on levels, for instance? Okay, no,
I can't comment.
Just a curiosity.
Yeah.
Thanks.
Okay, just a curiosity as well. I mean, you see the important role of lead. I mean, did you try tin, other metallic?
But it brings us to indirect semiconductors.
With tin?
We colleagues in Dortmund are measuring them, but physics is different because you have indirect band gap. So one need to start them to go there.
Okay.
But excitation, this is optical orientation protocols became different. You have a scattering to another value.
Yeah, okay. Okay. I don't think there are further questions. Let's thank Dim again.
Thank you.
And thanks to all the people that were here and those who are connected online.